Okay, yeah, so this is a presentation about earthquakes, induced earthquakes. And I usually start this presentation with this figure. Many of you might have seen it. So this figure shows something very simple, which is the number of earthquakes, cumulative number of earthquakes as a function of time in the continental United States. The earthquakes are, the ones that are selected are those that have magnitude 3 or higher. The reason is that that magnitude is large enough that you can be sure that all of the earthquakes going back to 1960, they have been recorded. Okay, so we have a complete set of magnitude 3 and higher earthquakes in the continental United States, starting in 1967 or 1968. And what you see is that for decades, this follows a straight line, right? So that means that the occurrence of magnitude 3 earthquakes has the same frequency every year. But then starting in about the year 2000, we depart from that straight line. And then around, in the 2000s, we depart again. This is a signature of anthropogenic activity. Which anthropogenic activity? So you can co-locate in space and time these, say, additional earthquakes with an operation of water injection in mature oil and gas fields in the United States. Okay, so that water that is being injected at high rates, at high pressure, water that is co-produced with the oil, is being re-injected with little characterization of the subsurface and at very high rates. And it is, as you can see, causing earthquakes. The clicker doesn't work, so I have to. Of course, this created the grounds for a lot of scientific inquiry and societal concern. Now, I'm selecting here a very influential study by the National Academy of Sciences on the potential for induced seismicity from a wide range, as we will see, a wide range of subsurface technologies. So this is all very good, but it really is when the New Yorker published a full feature article about it that now we can say, yeah, induced seismicity is a really big thing. The New Yorker, maybe in this part of the Atlantic, doesn't resonate, but on the other side it does. Okay, so let me kind of go through some of these technologies that have been linked to the occurrence of man-made earthquakes. So one, as I already mentioned, is wastewater injection, water that is co-produced with other fluids and that either has to be treated at surface or re-injected deep underground. I will perhaps pay attention here to this graph. This graph, I might find it amusing. So this is a number of earthquakes per year as a function of time in years. In California, you see this wiggly line, right? And the earthquakes are not so predictable, right? So you have a few more earthquakes and a few fewer earthquakes depending on the year. But we have kind of a constant rate of occurrence of earthquakes in California. And the solid line is Oklahoma, right? So Oklahoma at some point had a larger rate of seismicity than California, which is a tectonically active area. Some of the earthquakes, some of the induced earthquakes have been linked to the fracking, hydraulic fracturing operation itself. So they are sort of the exception, but in some cases, the operation itself has been linked to the occurrence of earthquakes. In fact, induced seismicity this is not a new thing, right? So if this is a paper from the 80s, but the knowledge that in geothermal fields, earthquakes would occur as a result of operation of the field, extraction of hot water or injection of cold water and co-extraction of hot water. In fact, the very sort of process of shear stimulation has to do with the activation, hydraulic activation of fractures and concomitant occurrence of earthquakes. And so you can see here a cross-section with earthquakes located as a function of space in the Geysers geothermal field, which is the largest geothermal field in the world. Other activities have been linked to the occurrence of earthquakes, for instance, underground gas storage. Right? So in many different parts of the world, underground gas storage of sometimes different gases have been linked to the occurrence of earthquakes. And even groundwater extraction has been hypothesized to be associated with the occurrence of earthquakes. We actually studied this, so this is not our work, but we did a modeling study of this particular sequence of earthquakes in southeastern Spain, in Lorca. Indeed convincing ourselves, this is unfortunately unpublished work so far, but convincing ourselves that the evolution of stresses as a result of groundwater extraction was very much in line with the destabilization of a fault that could have generated this sequence of earthquakes. To give you a sense of the anthropogenic influence or the anthropogenic activity here, the water level went down by, I think, 200 or 250 meters over the course of 30 years. Okay, so clearly there was a human footprint in the groundwater there. So just to sort of summarize, this is not a new figure anymore. This is from a review paper that dates back now 7 or 8 years. But I think it is very useful from the point of view of showing that induced seismicity cuts across the globe geographically, right? So here you have a world map, and you have balloons everywhere, and these balloons have different colors. Different colors are associated with different anthropogenic activities. Okay, so it is a rather kind of a pervasive and global phenomenon. So this is something that, of course, people are interested in and want to study. So we can start from the beginning. Right? So earthquakes occur as a result of a rupture of a fault. That should not surprise anyone. And there are two sort of key concepts that, of course, are basic and very familiar to many, probably most of you, that we're going to use throughout this presentation, throughout this lecture. One is the concept of effective stress. So when you have a porous medium that is filled with a fluid, when you load the porous medium, that entire load is not transmitted through the solid skeleton. Part of it is transmitted through the solid skeleton, part of it is transmitted through the pore fluid. So the effective stress is the part of the stress that is transmitted through the skeleton is roughly the total stress minus the pore pressure. So the pore pressure is giving you an indication of the fraction of the load that is being transmitted through the fluid. So that's one key concept that we're going to be using. The other one is the concept of frictional resistance, and this is also very intuitive. Now, if you have an object like this one, right, it has some weight, not much, because this is paper. And if I push from the side, very gently, the object doesn't move, but if I push harder, the object moves. So I overcome the frictional resistance at that interface between in this case, the slider and the underlying surface. So that frictional resistance or frictional shear stress could have an adhesion component or cohesion, and then it's going to depend on the effective weight that the slider is resting on the surface. Okay? So that frictional resistance is, again, an addition plus some coefficient that we call the coefficient of friction times the effective normal stress on the surface. Okay, so these concepts are going to play a role in how we characterize the stability of a fault, which is one of the things that we are interested in. So things are not complicated here. Now the world is three-dimensional, so we have a three-dimensional stress field and a three-dimensional pore pressure field, and we can project those fields onto the fault surface, this surface of discontinuity. So we will have the effective normal stress and the shear stress on the fault. Okay. So the effective stress on the fault we've already introduced, and the failure shear stress we've already introduced. So it is useful, and we will be making use of this quantity throughout the presentation. We can define what is known as a Coulomb force function or Coulomb stress. That is nothing else than a slight reorganization of this equation above. It is the shear stress, say on the fault, minus the coefficient of friction times the normal compressive effective stress. Okay? So this quantity is relevant because if we have increases, positive increases or positive changes in the Coulomb stress, that is an indication that we are destabilizing the fault. Okay, so say we are increasing the shear with the same normal effective stress. And what we can do is we can look at the ingredients of the Coulomb stress and then understand just by simple inspection what are the mechanisms that can lead to destabilization of a fault. Right? So if I just have a delta here, increment in Coulomb stress, and we look at the ingredients, what do we see? We see that destabilization can occur from a change in shear stress, perhaps say coming from tectonic shear. It can be derived, or it can derive from a decrease in the coefficient of friction. So we are weakening the fault, and this can happen by a variety of mechanisms, perhaps by increase in temperature or by motion of the fault itself, as we will see. Motion of the fault can decrease the coefficient of friction. This is very common, right? That once an object starts moving, it keeps moving. The frictional resistance is highest when the system is stuck. But we can keep looking and see that if we have a decrease in the compressive total stress, total normal stress, that leads to an increase in the Coulomb stress. Right? So if we are decompressing the fault, this can happen because of, for instance, coupling with the fluid. Say that we extract fluid, the reservoir, the subsurface contracts, and it unloads the fault. So that poroelastic unloading will result in an increase in Coulomb stress. And finally, we can have an increase in Coulomb stress by an increase in pore pressure. Right? So this is the more direct mechanism by which fluid injection can destabilize a fault. The pressure goes up, the effective normal stress goes down, and as a result, we destabilize the fault. Okay, so this is, I usually make the joke that this is not rocket science, right? It's a rock science. I gave one of these talks at Caltech where this joke was very appropriate. Okay, so the question that we're going to deal with most in this presentation is a particular one, which is the dependence of induced seismicity on the rate of injection or extraction. Okay? And there's some empirical field evidence that these two things are linked. Okay? So I will just go through some of the field observations. So high rate wells are more likely to be associated with earthquakes than low rate wells. I mean, that by itself can be by a variety of reasons. But another pervasive observation is that temporal variations in injection rates are correlated with the frequency of earthquakes, sort of for the same level of injection on average, those temporal variations tend to induce more earthquakes. And the abrupt increases in injection rates tend to shortly precede the occurrence of earthquakes. Okay? So this is something that we would like to understand better. It's not particularly well understood. And we're going to approach this with two disparate approaches. So on one end of the spectrum, I'm going to spend half of what remains in the presentation on very simplified minimal ingredient models that go after sort of the essence of this link between injection rate and occurrence of seismicity. These are, you could think of as toy models, but hopefully I will convince you that they incorporate enough physics that we can learn something from them. And then on the other end of the spectrum, we're going to embrace the messiness and complexity of the subsurface and develop three-dimensional models that we solve numerically, and we try to history match those models to best account for the data that we do have, and use those models to explain seismicity that has occurred, say in a post-mortem fashion, and also use those models to make forecasts for future activity. Okay? So two very different approaches. So let's start with the first one. I'm going to spend a little bit of time on this slide and the next. So we are representing a creeping fault segment as a spring slider. Okay? This goes back to the 60s, and it really is the essence of how earthquakes are understood today, as a stick-slip instability. You have a slider resting on a surface that is stuck, it's not moving. If it starts moving, that is grounds for, or is an analog for fault destabilization and the occurrence of earthquakes. So the basic physical model is this slider that is attached to a spring, and that spring is pulled from one end at a constant rate, at a constant velocity. That doesn't mean, as you can imagine, that the slider is going to move at a constant velocity. Right? It could be stuck for a while and then respond and move suddenly and so on. So this goes back again, as I said, to the 60s. What is different in what we are doing here is that this slider is no longer a rigid body. It is a hollow body that itself has some compliance represented with a vertical spring that accounts for the compressibility of the rock mass adjacent to the fault, and that is porous. It has a porous lid so that the fluid can be injected, the fluid mass in the slider can increase, and it can diffuse away, again representing that hydraulic connectivity between the fault and the rock mass next to it. Okay? So you see the various quantities that are involved in this description, and there are some equations that will model this system, the dynamics of this system. They look complicated, but they are not. So, because I have a little bit more time today than I have in this usual lecture, I thought that I would kind of demystify these equations. So the first equation is just a definition. It's a kinematic relation. Now that says that the velocity is the temporal derivative of displacement. Right? So velocity is the temporal derivative of displacement, which we can write in this way. And well, there is we are interested in the relative displacement, and therefore
Can you write larger?
I can. So this first equation simply says that the velocity is the derivative of the displacement. Okay? And again, we're taking relative displacement, so this is with respect to the moving reference of the end of the slider from which we are pulling. The second equation is Newton's law. It's force equals mass times acceleration. The acceleration is the derivative of velocity, right? And we have to say what the force is. So the force is going to have one component that comes from the spring. So there will be a spring constant, which I'm calling Ks, times the relative displacement. And there's going to be the frictional shear stress resisting that motion. So that is going to be some shear stress. Now, the shear stress, we said, is the coefficient of friction times the normal effective stress. So two things are important here. The first one is that the normal effective stress is given by the mass of the spring divided by the area, and we have to subtract the pore pressure or the fluid pressure in the spring. So that's one important aspect. The other important aspect is that the coefficient of friction is not constant. The coefficient of friction itself is a function of the velocity at which the slider is moving at with respect to the surface, and people have characterized lab experiments and determined that this is not enough. There has to be a dependence on some other hidden variable. It's called the state variable that we call theta, that represents some sort of state of the fault that captures the healing process by which friction can be restituted. So what is relevant here is that this law that we use for the coefficient of friction has to be able to capture what is observed experimentally. And what is observed experimentally is shown in this diagram over here. If you have two bodies and you displace them at a slow rate with respect to each other, there is a friction, shear stress that you translate into friction, that you can measure. If you suddenly move that relative motion to higher speed, what happens is that initially the coefficient of friction goes up and then it goes down and decays. And whether it decays to a value that is higher or lower than the initial one is going to tell you whether the frictional surface is strengthening or weakening. So if it weakens as a result of going from low speed to high speed, that is the grounds for a frictional instability, right? So it moves faster and the coefficient of friction goes down, so it moves faster and so on, right? Okay, so this is why this equation looks so complicated, because it's already embedded that dependence on velocity and the state variable in the coefficient of friction. Yes, Ron.
There's no need for the BO coefficient in the above equation there, minus p?
Yeah, no, so the BO coefficient I'm going to make, that's an interesting question. The BO coefficient, when it comes to frictional surfaces, most people accept that is 1. Now, for bulk deformation, it is not, and theoretically we know that it is not. But for the frictional response of a surface, what is understood is that the BO coefficient should not be the one that corresponds to bulk deformation. Okay, now, so we have a dependence on the state variable. So the state variable has its own equation. In the rate and state description, we will have an evolution equation for the state variable that depends on, well, the state variable itself, the velocity, and if we have a varying effective stress, it will have a dependence on it. And this goes back to some experimental work in the early 90s that demonstrated that for a dry system, this did not have coupling with fluid, but for a dry system, if the normal load, the normal stress was changing over time, that would have an imprint on the frictional resistance. And that was captured, it was modeled as a dependence on the state variable. Okay, so we're borrowing that or extending that concept proposed originally by Linker and Dietrich as dependence on the normal effective stress and therefore on the fluid pressure in the slider. And okay, so that describes the motion of the slider, but what is missing is the coupling with the fluid, right? So we have an equation for fluid pressure simply by mass conservation in the slider. So we will have for that slider that has a porous lid, we can have injection and we will have filtration of fluid out of the cavity if there's a pressure difference. So what goes in, Q, say per unit area, minus what goes out, which we can calculate by the Darcy velocity. So that will be some permeability of the porous lid divided by the fluid viscosity times the pressure difference, so the pressure in the slider minus the ambient pressure divided by the characteristic length of the porous lid. What goes in minus what goes out is equal to the mass that is accumulated. So we'll have the rate of change of density times volume. Maybe I can just leave it like this, the volume of fluid. Okay, so you can quickly rearrange this equation into an ODE that involves the evolution of fluid pressure. Yeah, okay, so this is just to demystify these equations. They come from first principles of Newton's law and mass conservation of the fluid, and some well-accepted model for the frictional resistance called the rate and state model. Yeah, okay, so it proves useful to write these equations in dimensionless form. This is useful for this problem and for many other problems, right? So we're going to have a dimensionless displacement and velocity, and the state is already dimensionless, and dimensionless pressure. And what we identify are 4 different dimensionless groups that I'm going to describe briefly. So we have one dimensionless number that is a ratio between 2 timescales. The inertial timescale, so imagine the vibration of the slider as a result of the coupling with the spring, that timescale, with respect to the frictional timescale, that is the timescale at which friction is restituted after a sudden change in velocity. So that's one that is relevant. And typically, this is a very small number, like very, very, very small, making these equations very stiff. Another dimensionless group is the dimensionless spring stiffness. Okay, and think of this spring that we're pulling from as being super stiff, made of, I don't know, carbon fiber. That leaves no wiggle room between the end from which we're pulling and the slider. The slider is going to be forced to just follow whatever the end from which we're pulling is doing. or it can be very soft, right? Like a very soft, wiggly spring. We also have the dimensionless hydraulic diffusivity. So here you see some of the parameters that you would expect, right? So for instance, the rigidity of the normal spring, so the compressibility of the rock is playing a role, and the permeability of the rock is playing a role. So this is the hydraulic diffusivity, dimensionless, and this is the dimensionless injection rate. Okay? And once again, you see the actual injection rate per unit area, and other properties that render this quantity dimensionless. So, yes, question?
Between the board and the map that you had there, was it just rearranging that got you to find the equations?
Yeah, just rearrangement. Yeah, so for this dimensionless version of the equations, you have to, well, introduce dimensions of length and dimensions of time, and you're left with these dimensionless groups that are the ones that go into the dimensionless version of the equations. But they are one and the same, just pure algebraic rearrangement. Okay, so here is the basic observation. We choose some values for these parameters, right? For the 4 parameters that I mentioned just now, and for the frictional parameters A and B. And we just solve these equations numerically, not with an ODE solver, a good one, because these equations again are super stiff. And for that choice of parameters, this is the particular evolution that we see. We have this is a case without fluid injection, and therefore the effective stress is exactly constant. And we see that for this choice of parameters, the velocity of the slider is more or less constant, so we have steady sliding. There's some small wiggles in the beginning, maybe reflecting that the initial condition is not exactly in equilibrium, but then it quickly moves to a steady sliding motion. And the acceleration is the derivative of the velocity, so it's almost zero everywhere, all the time.
Can I ask, what's the forcing here?
So the forcing is, as I said before, is tectonic forcing. We are pulling from the spring. Yeah, not really pushing the slider directly, but pulling from the spring. And we see that velocity with which the slider moves is very quickly exactly the same as the velocity at which we pull. Okay, so same parameters, identical parameters with one difference. We're now going to inject fluid into this hollow slider. So as we inject fluid, the fluid pressure goes up, and concomitantly the effective stress goes down. And now the response of the slider is completely different. So we see that initially the slider is stuck, and then it moves suddenly in a slip instability motion, and then it gets stuck again, and then it slips again, and then it's stuck again. So this happens for a while, and then after a while we go into steady sliding motion. Okay, so that shows, I think, two things. The first one is that fluid injection can change the behavior, the dynamic behavior of the system. That's one thing. The other is that there is a surprising switch in regimes. No, it's not like we are in the stick-slip regime all the time. We switch, just naturally the system switches to steady sliding motion. So that is kind of surprising. So we wanted to understand why this was happening. And this can be rationalized with a stability analysis. I'm not going to get into the details of the stability analysis, but the basic idea is that you perturb the system and identify the conditions under which those perturbations grow exponentially. And there's some choices, some technicalities that have to do with No, what is the base state that you use, in particular for the pressure field? So here we're using a quasi-steady state approximation, which has, now admittedly, some limitations or some range of validity, but as we will see, seems to be sufficient to explain what we observe with the full nonlinear simulations that I illustrated earlier. Okay? So what is the result of this stability analysis? I'm going to have to spend a little bit of time explaining this figure. So this stability analysis for dry systems go back a long way. This is a classic instability criterion by Ruben in the early 80s that says the following. It says that the system is prone to frictional instability, to this stick-slip motion, if the stiffness of the spring is below a certain threshold. And that, once again, I think intuitively it makes sense. If we have carbon fiber, there's no wiggle room for slip instability, stick-slip instability. We have to have some compliance of the spring for the slider to get stuck, as we're moving the other end of the spring and then catch up. So this is what this says, and that depends, so Ruben found, doing this stability analysis, that depends on the parameters of the rate and state law, B minus A, multiplied by the normal stress, which for us is the normal effective stress. But because without injection the pore pressure is constant, this term is constant. Okay, so we have this baseline here that says if the dimensionless spring stiffness is below this critical value, the system is unstable, frictionally unstable. If it is above, it is frictionally stable. This is, yes, Danny.
I want to...
No, on the contrary.
This goes back to the assumption that you have a spring.
Yes.
That means that you have, you neither have a constant velocity nor a constant stress on the slider.
Correct. That's exactly right.
Yeah. So I can convert the problem to an equivalent problem where I transfer all these ingredients into the interaction between the surface and the slider. For example, you can imagine and not too complicated fiber bundles that do similar things.
Yeah.
It is a product of the fundamentals of the initial model, and rather than some magical characteristic of the system.
So you raise, Danny Orr is raising a very good point, which I understand, if I may kind of do an interpretation of your comment. What is the origin of these parameters A and B in the rate and state, and the rate and state law itself? It would be great, so it is purely phenomenological. It is very well accepted in the seismology community, computational seismology community, because it is able to reproduce lab experiments very well, and it is able to replicate frequency magnitude relationships that are observed in the field. Right, so it is phenomenological, but it has that kind of validation component both in the lab and in the field. But the point that you raise is, I will bring it up a little bit later, is in my mind really exciting. So what is the micromechanical underpinning of rate and state or some other law that develops stick-slip instability? It would be very gratifying to link that to the micromechanics of the surface. This is not what we're doing here. Okay, but what we are doing here is extending this classic instability criterion to the case in which you have fluid injection. So what you see is that, okay, it takes a similar form. The pore pressure is now changing. So this is color coded. We have the old term, the Ruben part of the instability criterion, but we have a new term. And this is color coded in the sense that we have a dependence on pore pressure itself. If we inject, the pore pressure is increasing, And this is telling us that as the pore pressure increases, this term decreases. Okay? So we'll hold that thought. But there's another term that exhibits a dependence on not the pore pressure itself, but the pore pressure rate. Okay? And this comes from the Linker and Dietrich contribution to the rate and state law. And as we inject, the pore pressure increases, so the pressurization rate is positive, and therefore this is a positive contribution. So what is the result of this coupling with fluid pressure? The result is that at the beginning of injection, the fluid pressurization is high, but the change in pressure itself is low. So this red term dominates, increasing the threshold spring stiffness, that is making the system more unstable. Later in the life of fluid injection, the opposite is true. This sort of plateaus, the pore pressurization rate is low, but the increase in pressure is high, and this term dominates, decreasing the spring stiffness and therefore rendering the system more stable, frictionally stable. Okay? So this agrees with the observations from the numerical simulations, where we had an early period in which we had stick-slip motion and a late period in which we had steady sliding. Okay? So this is the result of the stability analysis. And in my mind, I think this is really, I know this is a cliche, but a minimal ingredients rationalization of this link between pressurization rate and frictional instability. So what we can do now is have a swath. I love phase diagrams and parameter spaces. So here's one. So let's freeze all the parameters, but leave two of them free. Right? Two of them is easier to show on a diagram. So we are leaving free the dimensionless hydraulic diffusivity and the dimensionless injection rate. And we run simulations at all of these conditions. We have a grid for all of these parameter combinations, and we run a simulation just blindly, 2 for loops, and we extract the maximum velocity experienced by the slider in each simulation. And we color code it, and what you see is that there's a sharp transition between regions of this parameter space where you have stick slip, you have sudden slip motion in red, and then other regions of the parameter space in which you have steady sliding. Okay? And this has some shape to it, and it turns out that the linear stability, so for instance, at low hydraulic diffusivity, at low permeability, the critical injection rate at which you induce instability is independent of permeability. But at high permeability, it depends on the permeability itself. The higher the permeability, the higher the injection rate has to be. And there's a one-to-one relation there. So these scalings at low permeability and high permeability are actually reproduced or explained straight from the linear stability analysis. Okay. So you may say, well, yeah, this is all nice perhaps, but it's a toy model. Right? Does this have anything to do with the real world? And that was indeed a question that a reviewer asked. So does this have anything to do with anything in the real world? So the way we thought we could address, at least in an incipient fashion, that question is by looking at a documented case in which we had as much information as possible to constrain the parameters in our model. So we chose this well-known sequence of earthquakes, the Rocky Mountain Arsenal earthquakes in the 1960s. And what you see here in this graph, this is from the original publication. You see the here at the bottom, the injection rate of fluid waste and the number of earthquakes. And this is binned monthly, I think, yes. So this passes the eye test, right? If we don't do anything, I mean, these two figures look alike. So there seems to be a clear influence of injection rate in the seismicity that is recorded. So what is, we use this field case or this historic set of earthquakes because we could find enough information in the literature to pin down the parameters in our model. Okay, within some ranges, and there's of course some translation that is required, but no, with the information at hand, we could say that the dimensionless hydraulic diffusivity could be within this range, and the dimensionless injection rate could be within this range. Okay, these are dimensionless numbers. So now we can look at this set of earthquakes from the lens of our model. Okay, and now you have to accept that viewpoint. But from the point of view of our model of a spring poroslider, injection rate can be deemed important in the generation of seismicity if it has a big enough influence on what we are using to describe the stick-slip instability, which is the critical spring stiffness. So does the critical spring stiffness change sufficiently for this set of parameters? And the answer is yes. Right? So we see that depending on the parameter values, it can increase by either 30% or 3,000%. So fluid injection, again, from the lens of our model, would say can increase how much the system is prone to instability. So that's one thing. And then the other thing we can do is to look at the parameter space, right, that I just described, and just simply plot the range of parameters that correspond to this field case. And what we see, interestingly, is that this square representing the field, the dimensionless parameters that correspond to this field case, no, this is right at the boundary between aseismic and seismic response. So, I mean, I interpret this as, well, within the confines of this toy model, it would be sufficient to explain the transition from no seismicity to seismicity as a result of injection. Okay, so then you can use this model in a variety of ways. No? For instance, what would be the best way to inject a certain volume of fluid? No? So you can inject at a constant rate for a period of time, but what that will do is that will result in an increase in the critical stiffness early on, as we've seen. You can inject the same amount of fluid, the same volume, in a shorter time. So in that case, the critical stiffness increases more, suggesting that you are destabilizing the system more. So is there perhaps an alternative? Yeah, you can concoct other injection strategies, no? For instance, one in which you ramp up injection and you let the pore pressure stabilize after each step. And in that case, you have many, but now smaller increases in the critical stiffness, suggesting that this would be a safer way to inject. And there's a question. Yes, Thomas.
Is there any reasonable way to define a curve that minimizes the critical stiffness?
Okay, so we haven't looked at that, but
do you think it's stupid on the sense of it, or do you think there's any?
No, I don't think it's stupid. Yeah, no, I don't think it's stupid. No. Yeah. Yes, John.
If your goal is fracking, then we have to essentially, expand the fractures. And so, just to check, this ramped injection actually would not serve the purposes of a fracking process.
So that I must say we haven't looked at. We will have to see how the tensile stress is responding.
If you're really separating rocks from each other, it's clear you've reduced the frictional forces.
Yeah, so fracking would involve a mechanism of tensile failure more than shear failure. And I mean, I don't want to give like sweeping statements. We would have to look at it in its own right.
There is probably spatial dimension to all of this anticipate.
I mean, this is a zero-dimensional model, right? We're going to see three-dimensional models immediately after this, right? But this is zero-dimensional. So there has to be some limit to...
So following on John, can you make some statements about seismic and aseismic, say, friction, unloading of loaded faults?
Yeah, so the kind of the generic quick statement that I could make is that if B minus A, which can be characterized in the lab, say, is negative, you are in an aseismic condition, geology, right? So you can have slip, but that slip will be of a creeping motion, not of stick slip motion. Now, if you are in a potentially seismogenic region where B minus A is positive, then this is starting to play a role. The coupling with the fluid pressure is starting to play a role, and we claim it is not only fluid pressure, but pressurization rate that also matters. Okay, yeah, so a gradual increase in injection rate reduces, not minimizes, reduces pressure rate destabilization. Okay, so what did we learn? Well, hopefully we learned something from this. And I love this type of models. I have to be honest with you. So we've continued to work to extend this line of inquiry. And one interesting way is to ask, well, how much energy is radiated? Because in an earthquake, it is the radiated energy that really matters, is the component that is really destructive. So you can think of this spring poro slider being connected to other sliders that, again, are linked by shear springs. You can actually reduce this model into a single degree of freedom. Again, I'm not going to get into it, but now you can count joules. Now, I worry a lot about watts in my other life. So this is what these are. This is an equation in watts. So there is a power, an energy rate of that goes in by fluid injection, and that is used into producing some work, into elastic energy that is stored in the skeleton, in the fluid, and some of it that is dissipated frictionally by fluid seepage. Okay, so that describes the energy budget in the fluid system, and at the same time you have the spring slider, right? So you're pulling from the spring, and you can do the energy budget for that too. Some work that is done by pulling, and that goes into the elastic energy in the spring, the frictional loss at the frictional surface, and then the kinetic energy in the slider, and the radiated, what is left is the radiated energy that goes into this sequence of shear sliders. And that's what you care about. So you can characterize all of that in this zero-dimensional model with interesting results, right? So it turns out that the seismic, some of the quantities quantities of interest that seismologists use, like seismic efficiency, stress drop, total slip, they are directly influenced by the pore pressurization rate. And indeed, fluid injection leads to bigger and potentially more damaging in the sense of having a higher fraction of radiated energy than purely tectonic earthquakes. Okay? So this all comes from that energy budget. And here I'm going to pay some homage to Danny Orr's earlier question. Does all of this depend on this magical rate and state law? So it turns out that not really. So is there an alternative description of friction that is simpler, please, than rate and state law? Yes. How about Coulomb friction, where the friction is constant? Right? That's simpler. But constant in time, but not uniform. So imagine that you have two rough surfaces, and this is work in collaboration with Jan Nordbotten, whom many of you know from University of Bergen. And so I'm borrowing his analogy here, which I think is very graphic, very visual. Imagine that you have a smooth surface, but you have some stripes of Velcro, right? And then you have the same smooth surface with stripes of Velcro, and now you slide one against the other. When you have the smooth surface against smooth surface, or smooth surface against Velcro, it is still going to be slippery. But when you have Velcro against Velcro, they stick to each other. So the coefficient of friction spikes up. So that is our description of friction here. We have the spring slider with heterogeneous but Coulomb friction. Like there's nothing simpler. And then you just solve the equations. And it turns out that you have this whole set of transitions from steady motion to different types of stick-slip instability that reproduce some of the scaling laws that are observed in the field in terms of things like duration of the slip event and magnitude of the slip event. Okay? So this is again just I would say sort of a heretical exploration of how simple models of friction may lead to complex frictional behavior. Yes?
Sorry, Ruben. So in this model, you don't apply the rate and state parameter, but you just change the friction coefficient.
Yeah, so, but we change it in a way that I think is physical. So you have these two surfaces. So this is shown here. So here we have relative displacement and a position, right? So in a Lagrangian coordinate system, you're following these stripes. So one of the surfaces is not moving, the other one is moving at a steady velocity, say. And well, if it's moving at a steady velocity, then these characteristic lines are straight lines. So now what we have here in this particular study is trying to replicate or reproduce this notion that it is only when you have Velcro against Velcro that friction spikes up. We have a multiplicative description of friction. Depending on the frictional state of both surfaces, a multiplicative model will give you a friction coefficient for the interface that is changing in space and time because it's moving. But locally, the friction is Coulomb friction.
You use a special heterogeneity, but then you get also a temporal variation
because of the motion. Exactly. Yes. But yeah.
Does this care a lot about how you distribute your friction?
No. Well, okay. Let me step. Not really. For simple, you can have sinusoidal variations. You can have step heaviside functions, and the type of transition that we observe is independent of that. Now, we haven't really explored perhaps more complex variations of friction.
So like a characteristic size of patches.
Yeah, all of that would be. Yeah. So that's an interesting question. If you buy into this, then how does the description of that heterogeneous Coulomb friction influence the overall dynamics? Yeah, so that we haven't looked at. Yeah. Okay, all right. So that's enough for zero-dimensional models. Let's go up 3 dimensions.
Can I sneak one more question? Are these more
Yes.
traditional models, are they chaotic, the stick slip systems?
So chaotic.
They have sensitivity to initial conditions.
So I would say, okay, let me think about that.
And then the follow-up is like, does that model also have sensitivity to initial conditions? If so. I wonder more about
Sorry, what's the follow-up question? Sorry.
does the Coulomb friction with heterogeneous,
Yeah.
does that have the same sort of dynamical system properties as the more traditional stick slip model?
Right. So what I can say with confidence is that you do have a sharp transition from steady motion to stick slip motion. But if there are different characteristics in the stick slip motion, say that will produce bifurcation behavior, that, to be honest, I wouldn't know. I wouldn't know myself, and I don't know if it has been looked at. For the heterogeneous Coulomb friction, we do see a sharp transition. So again, we see similar behavior, but in that case, I don't have an extra slide that I think would be relevant here, which shows the actual temporal dynamics of the slider for different choices of parameters. And you can see very nicely that there are different regimes, indeed, that we associate with ordinary earthquakes and slow slip earthquakes and low frequency earthquakes. But I would say that the transition is not of bifurcation type. It is gradual from one to another. I don't think you see chaotic behavior, not in this system. Again, to be confirmed or explored, but yeah. Okay, so I'm going to speed up. No. So in the 3D world, we still have the same equations, only that now they're in 3D. So we have fluid mass conservation like we had here, and we had linear momentum balance like we have here. And we solve fluid conservation if we have multiple phases for, say, fluid pressure and the fluid saturations, and the linear momentum balance equations for the displacement of the skeleton. And these two sets of equations are coupled, once again, reflecting the notion of effective stress, so that's the direct coupling. Changes in pore pressure will affect the deformation. And there's also a reverse coupling, right? If you ever squeezed a wet sponge, clearly mechanical deformation will induce fluid flow and changes in pressure. And it can also lead to also changes in reservoir properties like permeability, porosity. So, like, this is a big field, and people have been looking at coupled pore mechanics for a long time. And here I'm just, once again, paying homage to our early work on the subject. But a lot of different groups work in this space. The idea is that you can solve these two sets of equations. They're not easy to solve, especially if you have surfaces of discontinuity. You have to worry about the relative motion. You have to introduce additional variables in one way or another, as Lagrange multipliers or something similar, to be able to resolve those sharp discontinuities. But I'm not going to talk about that today. Instead, I'm going to talk about one particular field and one particular set of earthquakes. So the field is the Val-d'Agre field, which happens to be the largest oil-producing field in continental Western Europe. That is in southern Italy. We're here, right? So not too far. You can see this is a seismic hazard map. So you see warm colors here throughout the Italian peninsula, reflecting the well-known fact that this is a seismologically very active area, which makes things difficult. To illustrate that, this is the area of the largest recorded documented earthquake, at least in, well, modern times, the 19th century Basilicata earthquake, which was really devastating. Records indicate that there were over 10,000 deaths. The estimated magnitude was magnitude 7 for this earthquake. And if what I've been told is correct, and this is not an urban myth, I hope, the word seismology derives from this earthquake. So seismologia was the word that was used to study this earthquake, and then it was extended to the study of earthquakes in general. Okay, so that's just a trivia, FYI. Okay, so what I'm showing here is a plan view of the area with the outline of the producing oil field, and the red dots are located earthquakes. So here just the epicenters for a period of time between 2001 and 2006. Okay, so the maximum magnitude of those earthquakes is of this set is 3. So there are about 60 events of magnitude 2 and higher, just to give you a sense of the seismicity in the area. You see clearly a cluster of seismicity here outside the field, but right on top of a man-made lake, right? So this has also been very well documented. Variations in reservoir, but like surface water reservoir level, are the ones responsible for the, so that's another kind of induced seismicity. But we're not going to talk about that cluster of earthquakes today. But what you can see here is outlined in green is a region surrounding this well where water started to be injected in 2006. So I'm going to flip, if you look at the slide, I'm going to flip to the next slide, which is the cumulative set of earthquakes located, but now on a longer period of time from 2001 to 2018. So you see, I'm going to go back and forth one more time. So back, and now forth. So you see more earthquakes, well, because in the region there are more earthquakes because we've been recording for longer. But there's a new cluster, which is color-coded here in green, that wasn't there before, that is like right on top of the injection well. And that well started injecting in July 2006, right? So there's no question that this new cluster of earthquakes was generated by that water injection. And that is the cluster that we want to understand and work with. So just very generally, this is a field that started production in the 90s, very gradually initially, and then went through a rapid expansion. It is a complicated field, very complicated field. I'm not a geologist, and unfortunately I cannot really speak to what you see on the slide here, but I know that the Mediterranean Sea is, geologically speaking, has been a super active, super dynamic area. No, it was close to the ocean for long periods of time, multiple times. Lots of evaporation took place with concomitant precipitation, and then the refilling and all the tectonic forces from the various plates that converge around the Mediterranean. Anyway, it's a geologic, I don't know if to say mess or maybe not mess, beauty. It's a geologic beauty, right? But I will just say one thing, and that is that there are multiple sets of faults, the Monte de la Maddalena fault system, the East Agri fault system, the Caldarosa fault system, that we try to incorporate in what is known as a structural model, right? So a structural model is a digital model of that subsurface that recognizes the various horizons that are important and the various sets of faults that are surrounding and within the reservoir. You see here an outline of the Lake Pertusillo that I was referring to earlier, and the different fault systems. And here's a more detailed view of the faults, again mapped and interpreted from 3D seismic in more detail around the injection well, because that's the area of most interest. This structural model is the starting point for the computational model, the flow and geomechanics computational model. So this work actually started almost like 10 years ago. And at that time, so we have a domain size of in the order of tens of kilometers, 80 by 50 by 10. At that time, no, we were very proud that we had like 200 grid blocks. Of course, now we routinely have 20 million, right? But no, some time has passed, and we have ChatGPT now and whatnot. So maybe all of this will not be needed very soon, and we are in, that would be another talk that I could give. So this mesh recognizes the topography, the various strata, and all the faults that we had in the structural model, right? So you can see that even though it is only 200,000 cells, but there's a lot of complexity that is captured. Now here's a more detailed view around the injection area. So that has to do with how we represent the geology. So we do our kind of our best effort to represent it with some fidelity. Another complexity is the fluid system. So this reservoir is compartmentalized into three main, we could call them sub-reservoirs. Also very complex because they have different fluid properties that are not in equilibrium. So all of that has to be characterized, and it has to be incorporated to a flow model that then matches the data, right? So there was a huge effort, really, that I'm not paying any justice, I'm not giving any justice to, but to be able to match the pressure response at the production wells. So that has to do with the fluid flow model. And then with regard to the geomechanical model, we will have sort of this domain that on which we will impose the tectonic stresses that we know with, actually in this case, with some level of certainty what they are, right? So it is a normal faulting system currently, even though many of the faults are originally reverse faults, right? They were generated in a completely different tectonic regime, but we have normal faulting currently. And you can see here sort of pictorially the different regions in the flow model and how the flow model is embedded into this larger geomechanical domain. So to make a long story short, we have a flow model that produces pressures in space, 3D, and time. And those pressures, remember effective stress, are acting as internal loads in the geomechanical model. And by solving the geomechanical equations, we can compute the evolution of Coulomb stress on all of the faults that we have in the model. Okay? So that's the gist of it. And this is the one figure summary of all of that shows the variation in Coulomb stress on all the faults in the model between the beginning of production and the end of 2016. So this is color coded, and what you see is that almost all of the faults are predominantly and vigorously stabilized. You see cool blue colors, right? Here you see a color bar. So we are, because of oil and gas production, the pressure is decreasing, and that is stabilizing the faults, except for, well, the Costa Molina fault that is sitting right next to the injection well that is strongly destabilized. And we can see, so this is just a snapshot in time, but we can look at what happens over time, at least in a few, at a few discrete times. So let me explain what you're looking at. What you're looking at is a histogram of Coulomb stress on this Costa Molina fault that is generating the earthquakes. So before injection starts, you see this histogram to the left of zero, right? So this fault has been stabilized up to that point. It has negative Coulomb changes in Coulomb stress. Yeah. Now So this this label, this should be June. Okay, so this is May, this is June. So injection started in June of 2016, and very quickly we send this histogram to the right. Right. So we are very quickly destabilizing this fault. The regulator says, well, you're generating earthquakes, you have to stop injecting. So you stop injecting, and then very quickly the histogram goes back to being negative. And then you say, well, you can restart injecting again, and then this histogram goes back to the right. So this yo-yo motion clearly is linked to injection. I am not really, I won't have time to describe modeling efforts that were interesting in that they include additional physics. So we have a sector model, smaller domain, that uses the bigger regional model as to provide the boundary conditions in stresses and pressures. But the additional physics come from having the ability to model the slippage on the Costa Molina fault. And then you have, even in a Coulomb stress or Coulomb friction view of the world, you have one additional parameter, the static friction. So you can calibrate it. You can calibrate the static friction so that the cumulative moment on the fault matches the cumulative moment from the seismic record. Okay, so this is I think of interest in itself, but I'm not going to spend more time on it. And I will just go straight into sort of the synthesis of the analysis, which is summarized in this figure. So we have injection rate in that injection well, Costa Molina well, that started in 2006 and was fluctuating and very quickly generating earthquakes, but it's not clear what the link between the number of earthquakes and the injection rate is. But if we parse this through the model and look at the Coulomb stress on that fault, what we start to see is that the most vigorous earthquake activity occurs when you exceed a historic maximum in the Coulomb stress. Okay, so this is, I think, sort of an interesting modeling output, that new maxima in the Coulomb stress on the Costa Molina fault seem to correlate very nicely in terms of timing with the most vigorous seismic activity. And the same happens to be true for this sector model.
Ruben,
yes?
Isn't that a bit circular?
Okay, in what way?
Of course, when you exceed the maximum, you should see. So the definition of the maximum should come somewhat independent of what you observe, right?
It is independent.
But
so
you're matching it.
Oh, no. So we are matching, so we are not matching, right, so we are not matching in this curve, the coefficient of friction is matched, you're right, but in this curve the matching is only on the pressure field. Yeah. So there's no attempt to match the occurrence of earthquakes in this curve. It's sort of an observation that is a little bit hypothetical, right? So why fundamentally exceeding historic maximums in Coulomb stress be responsible for generating earthquakes? Some people actually have hypothesized that this would be the case, and seems to apply here, but I wouldn't say it's sort of a fundamentally grounded link. But what we can do now, yes?
What are the parameters used to calibrate the model?
So everything, and mostly permeability. So you have some geostatistical generation of the permeability field grounded on where you have hard information and grounded on well logs and things of that nature. And then you use that as the starting point, and then you have permeability multiplication factors here and there to try to match the history the best you can. Yeah. Yes, Ran.
Is it two-way couplings or is stress effect?
Not here, no. And we feel that the reverse coupling was not so important here. You can compute the coupling strength. It's a parameter that derives from the equations. And the coupling strength here was less than 0.1, actually more like 0.05 or 0.01 in most of the reservoir, making us feel comfortable with the choice of having just one-way coupling. In other cases, that's not true, but in this case, it seems.
The uncertainty and permeability doesn't make sense to invest so much in the cross-coupling.
Yeah, in this case, I would say that's true. Yes.
Now that everybody is asking, can I ask also? So here, when you reach the critical CFF, do you have a kind of sequencing model or rate of model, or is it just okay? We have reached the failure and then we continue to inject.
Yeah. No. So I'm gonna tell you more about. You've exceeded. You will not inject anymore. I will talk about.
My question is, when you reach failure, does failure occur? Do you have static stress transfer, or it's like a poroelastic model?
Not in this model. So in this model, we do not have that poroelastic. We don't have slippage of faults, either quasi-static and certainly not dynamic. It is very simplified. Yeah. So, but what we can, but the model we feel has some merits in that it has geologic fidelity, can match the pressure history, and we can use it to seemingly better understand the occurrence of earthquakes generated in that fault. So now we're really going to test the ability of this model, like for real. So we're charged with making forecasts. Forecasts are a difficult thing it's an easy thing to do, it's a difficult thing to get right. So the operating company had forecast models for the production history. Okay, so we incorporated that, looking into the future until 2046. Read into that what you may. And we said, as a result of that analysis, we ran a variety, but let me just describe 3 different scenarios for 3 different injection rates at Costa Molina. Because the big question was, can we continue to operate and continue to inject in this Costa Molina well? The alternative was really not a good one for the operator. They would have to, because of other constraints, not even treat the water that was being produced on site. They would have to truck it. Think about carbon footprint. Truck it, I don't know how many tens or hundreds of miles for other geopolitical constraints. Anyway, so we have 3 different injection scenarios. One at 2,000 cubic meters per day, 2,500 and 3,000. So that is reflected here in the proposed injection rate for a period of time between 2017 and 2019. So we made the recommendation to the company to operate at 2,000 cubic meters per day, based on the fact that for that scenario, you would not exceed the historic maximum in Coulomb stress. And it seemed to be like a sustainable, but at the same time conservative option. So that's the beauty of this, is that that's what they did. The operator operated at that target injection rate of 2,000 cubic meters per day for 18 months or 2 years. But of course, in the real world, you cannot stick to 60 miles an hour exactly, right? So there were periods of time in which they deviated from that target, and so earthquakes were essentially absent during that period, but they seem to coincide precisely with the periods of time where they deviated from that target. Okay, so this is in our mind kind of a unique opportunity of validation of a model where you not only try to make a post-mortem assessment of what happened, but use the model in a productive way to find operational strategies that would limit the propensity or the probability of earthquake occurrence. So we were so excited. I'll tell you about what the group was in a moment. I'm almost done. We sent this to like a high-standing journal, and one of the reviewers said, "Wait! But didn't you say that all of the surrounding faults were being stabilized?" That was a good point, right? So are they? So we looked into that, and indeed, so what you can do is you can take all of the faults in the region and compute the average. It doesn't really matter what average you compute, but the average change in Coulomb stress. And as a result of net production in the area, the Coulomb stress goes down. This is this black curve. And now you you remember how we started this lecture with the cumulative number of earthquakes over time? So historically, the number of earthquakes, cumulative number of earthquakes follows a straight line. But as you start production and you start decreasing the Coulomb stress, then the number of earthquakes in the region starts to plateau, right? So clearly indicating that you're stabilizing the seismicity regionally as a result of production. Okay, so indeed confirming that model output or model prediction of stabilization of regional faults is indeed reflected in the seismic record. This raises all kinds of questions, which I'm sure. So what happens when you stop production, right? Okay, so these are the conclusions. So sophisticated, I'm going to use, hey, I'm giving the talk, right? So I can use whatever words I want. So there's a sophisticated 3D couple flow geomechanics model that tries to, I would say the most interesting aspect is trying to reflect the geology with some fidelity. We use it to explain the source of seismicity in the Costa Molina injection area, and then we used it to produce some forecasts, and those forecasts were validated in the field by the operator. Something that most often you wouldn't have the opportunity to do. And I would say, again, because I'm the one giving the talk, right? So I said that this could provide a blueprint for how to manage induced seismicity, and this was illustrated in this particular case. And I will close the talk by saying that this was a very, very close collaboration between a team of academics. You can see some of the institutions here, including Harvard and Riverside and UT Austin, and a group of scientists, geoscientists, and reservoir engineers from the operator, the Italian energy company Eni, that they were from the very beginning sort of very open. There was a clear link between injection and seismicity. They were super open about it, and excited about the prospects of finding out what were the root causes and how to best manage that situation. So I would say that is the biggest highlight, that collaboration of academics and industry that made this work possible. With that, I will close and take questions, more questions if there are any.
you again for coming to Juanes and for a nice presentation. Now, does anyone have some questions?
I have maybe a controversial proposition. What would you say if we would use injection as a way to stabilize the regions? So for example, in highly seismic active regions, I don't know, Japan or Los Angeles or something like that, if we would inject and control the seismic activity, doing little earthquakes instead of having one disastrous.
I love the idea, and I hope, no. I love the question. And it's one that has not gone unnoticed by me and by others. Is there, if I may rephrase, can we use controlled injection to turn what would be a magnitude 8 earthquake into 10 magnitude 7 earthquakes or 100 magnitude 6 earthquakes? I mean, that would be terrific. But so I think it is worth, let me put it this way, I think it is really, I mean it, I think it is really worth exploring in controlled environments before you explore it in the San Andreas Fault. No, because it's earthquakes are understood as a self-organized criticality phenomenon. Small actions have unpredictable consequences, and you don't want to be signing at the bottom line. I think I don't want to be, you may, but I don't want to be signing at the bottom line on perturbing the system and then causing a magnitude 9 earthquake, which we understand could happen. But then statistically, yes, I think you could turn perhaps a magnitude 9 earthquake into a number of smaller earthquakes.
Maybe then simulations could come here handy and do some predictions of how.
You have too much.
So for the video, this was Danny Orr is saying that you have too much confidence in simulations.
Maybe you can inject, like you inject for the bike wheel, this viscoelastic glue. So you can inject that. to go tubeless. So, yeah, you turn tube into tubeless. John.
Excuse me, I'm just coming back from Africa, so I'll use the elephant analogy. But the elephant in the room is that there was a factor of 20 increase in seismicity in the United States between 2006 and 2012-ish.
Yeah.
And that was due to fracking. And fracking, really, I don't think...
So it was not due to fracking?
Well, I mean, it was a remarkable coincidence between
the
long history of 20 earthquakes per year going to 1,000.
But it had nothing to do with fracking. It had to do with re-injection of wastewater, not fracking.
Well, okay.
No. I think it's important to make that clear. It was not the fracking. The fracking operations had their own issues, and exceptionally, seismicity was linked to some fracking operations, but that dramatic increase in moderate to large magnitude earthquakes was due to wastewater reinjection, mostly in Oklahoma and Colorado and Texas.
Was it an aquifer recharge type? Or?
No. So this was mature. It's important to make this clear so that everyone understands. There were a lot of mature oil fields in the US that were for the longest time deemed uneconomical. But that, and why? Well, because the water cut was 90%, meaning that you would extract 1 barrel of oil and 9 barrels of co-produced water. So it was uneconomical. But some oil companies decided, well, maybe that's not so. We can just keep pumping out the fluid and then re-injecting, separating, which is a relatively inexpensive operation, then re-injecting the water. And the root cause of the problem was that re-injection was done, if I may use the word, carelessly, without much characterization of the subsurface. So for instance, a lot of the water was re-injected very close or straight into the basement, the crystalline basement, which is very seismogenic, and at very high rates. What you would produce, say, from 10 or 20 wells, you would re-inject into one, right? So they were very high rates, very high rate wells. So that was the bulk source of the anthropogenic seismicity, not fracking operations. I mean, I'm just saying that to explain.
They're distributed all across the United States. So I mean,
but say that plot in Oklahoma, where indeed you saw this 20-fold spike and exceeding the seismicity in the state of California, that was linked to the reinjection of co-produced water. Yeah. Now, how was that resolved? Well, that was resolved by better characterization of where you inject and injecting at more moderate rates and with some consideration for the for the geomechanical effects that has.
So you're claiming that the fracking per se, where you inject actual sediments into fissures and you create fissures and you totally change the frictional coefficient, that's not what was behind it?
Not these magnitude 3 and above earthquakes that were so pervasive during that decade or 2 decades. Of course, fracking operations will always, I mean, any affection of the subsurface will often generate some level of seismicity. But for the most part, the earthquakes that were generated by fracking were of magnitude -2, -1, 0 perhaps. In some cases, they activated some bigger faults. That was geothermal, but there's some cases in the US and Canada and other places where the fracking operation itself was linked. But for the most part, that was not the leading cause for that massive increase in seismicity at a continental scale. Yeah.
Just going back to the very beginning, where you were very nicely explaining the first critical equations and so on. So you mentioned when you non-dimensionalize, then you have this first non-dimensional group, and it's a ratio of typical time scales, and some natural oscillation or relaxation, I don't know, time scale.
Yeah, so that's a
There is these 3 parameters that was in your equations on the slides when you were on board. I wonder, how do you estimate this natural
very, very good. Yeah. So let's see here, right?
You're disconnected.
You just lost
Sorry. Yeah, I was these parameters. Yes. So right. So here, what you see is the period of oscillation, which is roughly the square root of the spring stiffness divided by the slider mass. Now, what is the spring stiffness? The spring stiffness has units like in Hooke's law, newtons per meter. That is related to the shear modulus of the rock adjacent to the fault times some characteristic length of the kind of the decay of radiated energy from the fault. So that will give you the link with the field. And the mass, similarly, it would be the density of the rock times that characteristic length.
So this characteristic length is fundamental, but it's probably hard to estimate in a complex fault system. How do you do it?
I agree that there's another characteristic, just to emphasize that point perhaps from another angle. There's another characteristic length here in the porous lid, right, that is serving kind of the hydraulic length over which you have pressure changes. Right? So these are things that you have to sort of estimate.
From the data capacity dense?
So for instance, you can use the interfault length as your characteristic length, for instance. I can't remember in the case of the Rocky Mountain Arsenal what we used, but I think it was something like that. no, it's a faulted system, and we were using that characteristic fault distance as our characteristic length. But you do need one to translate physical parameters, which are bulk modulus and shear modulus. They do go into parameters in here, but you do need, for instance, a characteristic length. Yeah, it's a good point.
So what is the mechanism causing one fault is become unstable in your case and all the other faults are stable?
Okay. Right, so that is something that I did not talk about at all, and we haven't incorporated in our models at all, but is known to occur. Now you can have both static and dynamic stress transfer. So the slip on a fault is going to perturb the stress field around it, and it may stabilize or destabilize other faults. Right? So you have, have normal motion here that may destabilize another fault down the line. So this is well known, and there are a number of earthquake sequences in which I would say with confidence this has been proposed as the leading mechanism for that sequence. We have not incorporated any of that. Yeah, it would be, I mean, in an ideal world we would be able to extend this work that we've done by enriching the amount of physics that we account for, like dynamic faulting, dynamic stress transfer. We haven't done it. Yeah.
Yeah, I think we have time for one more question.
So, based on that last answer and also your answer to Sylvia and what you were saying before, if I understand right, like I really like zero-dimensional models as well. But if I understand right, when you go to the sophisticated models, what really matters is the characterization and the geology. Is that true or not really? Like how much actual fault physics do you have to put into the
So I still think that so I would agree that reproducing the structure, the geologic structure, is leading order. But I think that representing the hydraulic response is also leading order. Right? So if you remember those snapshots that I was a little bit joking about, you have the histogram moving to the right and then to the left, and getting that timing and that pressure response from injection, that seems to me like also really important. So I wouldn't say that geology is enough. I think geology and subsurface flow are both important.
Well, thank you very much.